Although operations in decimals are very similar to operations in whole numbers, there are some very distinct differences that we need to make sure we teach. And most of those differences have to do with the language that we use. Also, we don't want students adding, subtracting, multiplying, and dividing decimals with only digits unless we're sure they really understand what decimals are. That means, again, working with manipulatives and working with diagrams and pictures so that they know the meaning of decimals. Too often when we teach adding decimals, we don't teach the meaning of the math. Pause the video and add these two problems and talk out loud. What kind of language would you use to make sure that you are explaining your thinking and that you're thinking about what each number means? So what do we want students to think? First, we want them to think I have 3 wholes and I have 5 wholes, so my answer is going to be about 8. I have 4/10 and 6/10. And here I have 7/100 and I don't have any hundredths up here, and nothing there is the same as a 0. 0 and nothing mean the same. So now I can add my hundredths. 0 and 7 is 7. 4/10 and 6/10 is 10/10. We want students to know from previous learning that 10/10 is a whole. So they're going to have to put that with the whole, which means they don't have any leftover tenths. Now they're adding the whole numbers. 1, 3, and 5 is 9. 9 wholes means the decimal goes here because I'm separating my whole from my part, and my answer is 9 7/100. In this problem, we need students to think the same thing. First of all, we have 8 wholes and 1 whole, which means my answer is going to be about 9, and then we want them to add. They can remember that every whole number has an invisible decimal, so I can put a decimal there. I'm adding tenths here, so if I want to, I can say I don't have any tenths, I don't have any hundredths, I don't have any thousandths. In this number, I don't have any tenths and I don't have any thousandths. For some students, putting the zeros will help them. Other students may not have to do that. Now I can add like things. I have 6 thousandths, 0 hundredths, 8 tenths, and 9 wholes. My decimal goes here because it's separating the whole from the part, and I would read my answer 9 and 806 thousandths. That and is so important, and this is why we don't want to be saying and when we teach students whole numbers. We want them to understand, especially when they're young and just learning, that and is separating whole from parts, and we save that for decimals so there's no confusion. All of those things we just talked about with addition apply to subtraction as well in most cases. We still want students to read the number, we want them to know what the decimal point means, we want them to think about the meaning of the math. Subtract these two problems, pause the video, and when you're finished, start the video again and see if the language that you're using as you do these problems aligns with mine. This number is 5 75/100. I have 5 hundredths and I want to take away 6. I can't do that because I don't have enough. So I'm going to go over to the tenth and I'm going to take one of those tenths. That means I now have 6 tenths. I'm going to break that tenth into smaller parts. I'm going to break it into 10 hundredths. I already have 5, so if I add 10 more, I now have 15 hundredths. 15 hundredths take away 6 hundredths is 9 hundredths. 6 tenths take away 3 tenths is 3 tenths. 5 whole take away 1 whole is 4 wholes. So my answer is 4 and 39 hundredths. For the next problem, I have 8 and 5 tenths, and I want to take away 2 and 38 hundredths. If students understand that they can only add and subtract like things, there should be an alarm going off in their brain right now because they said the word hundredths in the second problem and they don't have any of those in the first problem. So even if they put a 0 there because I have 0 hundredths and I need to take away 8, they're still going to have to do some trading. So what they're going to do is they're going to take one of these tenths, so they now have 4 tenths. They're going to take that tenth and break it into 10 parts, which means they now have 10 hundredths. Take away 8 is 2. 4 tenths take away 3 tenths is 1 tenth. 8 wholes take away 2 wholes is 6 wholes, and my answer is 6 and 12 hundredths. Again, as with adding, we don't want to talk about lining up the decimal. We want to talk about like things being together. We can only subtract like things. Wholes from wholes, tenths from tenths, hundredths from hundredths. If we've taught fractions well, multiplying decimals will be easier for students in terms of the language. Multiply these two problems. Pause the video and see what kind of language you're using as you complete these, and then check and see if your ideas are similar to mine. One of the first things we want students to understand in multiplication of decimals is why the decimals don't have to be lined up. We've talked about that in adding and subtracting. Why is multiplication different? In multiplication, remember that we have a number to start with, and we are taking that number a certain amount of times. So that second number really isn't representing a quantity. We're not adding or subtracting like things. We have one amount and we're doing something with that amount. So in multiplying and teaching rules and procedures, we can start with simple multiplication like our students already know how to do. And we can actually tell them if we want, let's ignore the decimal until we get our answer. And then we'll come back and see what those decimals mean. So 3 times 4 is 12. We're just using rules and procedures that we know from multiplication that was taught earlier. 3 times 6 is 18 plus 1 is 19. 3 times 3 is 9 plus 1 is 10. Now we want to go back and look logically, think logically about what we have. We have 3 wholes and we're taking them times 3/10, which is less than half. So our answer needs to be less than half of 3 wholes. What would half of 3 be? It would be about 1.5, and our answer needs to be less than that. Where can we put the decimal where that will be the case? The only place is right here. So our answer is 1 and 92 thousandths. If we look at the next problem, we see something that for students can be a little confusing. This is a good time to think about the fact that multiplication is commutative. So we may want to write this problem like this, just to make it easier for students to calculate and work with the numbers. 5 times 5 is 25. 5 times 7 is 35, plus 2 is 37. Now we look at what we have. We have 5, what we started with, and we're taking it 75 hundredths times. That's more than half, but less than 1. So half of 5 would be 2.5, and 1 times 5 would be 5. So our answer needs to be somewhere between 2.5 and 5. The only place we can put our decimal where that will be the case is after the 3. So our answer is 3 and 75 hundredths. After students have done many problems like this, where they've used logic and reason to put that decimal point in their answer, then we might have them discover what the pattern is. For example, if I had 30 students in my class, I might have them work in teams, so I have 15 teams, and I might give them each a different multiplication problem with decimals. And I might have them put their answers and their problems up on the board and see what we can discover. Oh my, look at this first one. We have after the decimal point 1, 2, 3 places. Look what we have here. 1, 2, 3. Here we have 1, 2 places after the decimal. And how many numbers do we have after the decimal in our whole problem here? 1, 2. And students can actually discover that this just works. If they add up those places, it's going to work out. But we want them to know that if they forget that rule, they can use reason. In long division, we can use what students already know about long division, and we need to make sure that we make a difference, a distinction between dividing by a whole number and dividing by a decimal. Because if we're dividing by a whole number, the division really isn't that much different until we get to the end and we're thinking about how we are going to name this answer. So for example, if we've taught procedures in division, we can say to students, how many 2s are in 6? 3, and that's really 3/10. How many is that? 6. We subtract, we've used all that up. Now we want to see how many 2's there are in 5. That's 2. We subtract because there's one we haven't used yet. And then we're going to bring down the next number because we haven't used that either. How many 2's are in 13? And the answer would be 6. 6 times 2 is 12, so we have one we haven't used yet. So now we have a couple of questions. What do we do with that decimal point, and what do we do with this remainder? So students need to understand a couple of things here. They could put remainder 1. That wouldn't be technically wrong. They could put 1/2. That wouldn't be technically wrong. But because we have a decimal, we want to try to stick to one thing if we can. So first of all, let's think about what happens with the decimal that we have here. We want students again to be able to estimate. How many 2's do they think there are in 65 and 3/10? If they just estimate, the answer would be about 32. So we know that we have to put our decimal in a place that gives us about 32. Now we can go back and say, well, what are we going to do with this 1 down here? Well, sometimes we can say to students, let's just put a 0 here because 0 is the same as nothing. It's not changing anything. And let's bring that down and see if we can keep going. Because here we had a 10th, and here we have 10 hundredths, which is really the same thing. How many 2's are in that? 5 hundredths. 5 times 2 is 10. We subtract, and we get nothing. Now we don't have any leftovers to worry about. Now we don't have any fractions to worry about. Now we have our number expressed as a decimal. Of course, if it doesn't come out even, then we need to talk to students about how they would represent that leftover. Would we want them to round? Would we want them to express it in some other way? If so, we have to handle that directly. Once we move to division by a decimal, we have a whole different kind of problem. We can say to students, dividing by a decimal is kind of difficult. We could think this is 2/10. How many 2/10 are there in a whole? 5. That means there's going to be 5 of these in every whole in our number. So we could figure out the answer that way, but it's kind of difficult. So here we want to have students use things they already know to make this easier. But we need to convince them first that what we're teaching them will really work. So what we're going to do is we're going to multiply this 2/10 times 10. 2/10 times 10 is going to give us 2. That means we're moving this decimal to the end of the number. But if we multiply that times 10, we also have to multiply what we have inside our box times 10. 65 times 10 is 650. So our answer will have to be around that. We haven't considered the 3/10, but it will have to be around 650. So if we move our decimal one place to the right, we will have 653, which probably makes sense. So now we've kind of gotten rid of this decimal, and we have moved this decimal over here, so it's no longer there. We've done the same thing to both numbers. It's best to make sure that students understand with whole numbers first that this will really work, that it's the relationship that's the same. We aren't changing the value of anything in terms of the relationship if we do the same thing to both numbers. So for example, if we have students look at this and then look at this and say, well, what if we take this times 10 and this times 10 and then divide? Will we get the same thing? Well, how many 2's are in 50? 25. How many 20's are in 500? 25. So we can have kids understand that the relationship is what counts, not the specific numbers. And that's exactly what we're doing with this division problem. So now we can divide and say, how many 2's are there in 6? And the answer would be 3. And now that 6 is really in the hundreds place, so it really means 300. And we can continue with our procedures that we've learned. How many 2's are in 5? 2. That's actually 2/10 now. And we subtract and we continue. How many 2's are in 13? 6. Sorry for the messiness here. And when we subtract, we get that remainder 1. So now we have to say, well, we could bring down another number and get that 5 again. And then we need to think about where that decimal will go. We started with 653 after we made the changes, and we wanted to know how many 2's were in that. Well, half of 653 would be about 300 something, so we know that our decimal has to go here to give us 300 something. And later, again, we can have students discover this idea that the decimal is going to go directly above where we had it when we started to divide. The decimal goes directly above because that's just how it works out. But we want them to be able to do that with logic and estimation before we teach them that rule. So if they forget the rule, they can figure it out through the meaning of math. We've already talked about mixed numbers, mixed decimals in operations, but I think it's important for us to end up with what are the important things for students to know as they complete problems like this that have whole numbers, mixed numbers, and decimals. So complete these problems and think about what you think it would be important for students to know as you complete these. Pause the video and then see what you think. With our first problem, I think the most important thing is there's a number there with no decimal. And we can make sure students know that every whole number has a decimal. It's just invisible because it's not needed. So they can put that decimal there if they wish to. And they also should know that this empty space is the same as a 0. And they can write the 0 in if it makes that easier. Then we're adding like things, which is why we put the decimals in a line. We're adding tenths and tenths, wholes and wholes. In subtraction, it's the same thing. We need them to understand that there is a decimal there, it's just invisible. And these empty spaces are the same as no tenths, no hundredths, no thousands. And then they can use their rules for trading, for regrouping. I take a whole and I make it 10 tenths. And then I take one of those tenths and I give it to the hundredths, so I have 10 hundredths, and I break that up, take one of them, break it up, give it to the thousandths. Now I have 10 thousandths, and I can subtract. 10 take away 6 is 4, 9 take away 0, 9 take away 0, 5 take away 2. My decimal goes here because it's separating the whole number from the parts. And I'm subtracting like things. I'm taking tenths away from tenths, hundredths from hundredths, thousandths from thousandths. When we multiply, we can just do the problem first. 5 times 7 is 35. 5 times 4 is 20 plus 3 is 23. I'm done with this number. I put a 0. I cross out this. I don't need it anymore. 2 times 7 is 14. 2 times 4 is 8 plus 1 is 9. I add them together and I get this. Now the question is, where does my decimal go? What does that problem mean? I started with about half, and I'm taking that half 25 hundredths times. That's a fourth. So I need to put my decimal here because if I put it after that first one, I will have a whole number. And I know that my answer has to be very small. And again, after we've done several of these, students can understand they're just adding up how many numbers are after the decimal point. 1, 2, 3, 4. So that's how many numbers have to be after the decimal point in the answer. 1, 2, 3, 4. What do we want them to understand in division? Dividing by a decimal can be kind of tricky. We can estimate, and a lot of students might say, well, I think I can do that. For example, here I can say this is about 4, and I think there are about 6 4s in 25. So I think my answer is going to be about 6. Now, that's good thinking, but when it comes to doing the exact division, it can be complicated. So we can say to students, let's just get rid of that decimal. Let's keep our relationship the same by multiplying this times 10, which means the decimal's now over here, and taking this times 10, there's where the decimal is now. 25 times 10 is 250, so the decimal has to go over here, and that's where the decimal is now. Now I can use my estimate, and I can say, well, I think there were about 6. 6 times 6 is 36. 6 times 3 is 18, plus 3 is 21. I'll subtract to see how many I have left that I haven't actually divided yet. And I have 34. Now if I think my answer is about 6, That means my decimal is going to go here, 6 whole. Then I have to figure out, what do I want to do with that 34? I could add a 0, bring it down, keep dividing, or I could estimate, or I could have students round. That would be my decision as a teacher. So as we think about decimals, it's the language that counts. Where is that decimal? What does that decimal do? What's the value of the number? How can we estimate the answer? We want to get away from things like, remember to line up your decimals, or remember the decimal goes straight up, or remember, count the places after the decimals when you multiply, because students may forget those rules. It's fine to teach them once the meaning of the math is there and understood, but they should always be able to go back and find the answer through reason if they forget the rule.